Good afternoon, everyone, and welcome to the party. I mean, the competition. So I wanted to give you a brief overview of the competition and the criteria. But to start with, each department nominated a project in their own department to represent them in this competition. So in this sense, every one of the teams have already won. So congratulations to the teams, and a round of applause. So the judging criteria for the best project is based on a number of factors: technological innovation, originality, engineering design quality, feasibility of actual implementation, social impact, and oral presentation. So the judging process actually has two phases. The first one is a detailed poster presentation, and where the judges were grilling them, I heard screams of pain. But no, seriously, so they had a very detailed 20-minute session with the judges. And then you have the formal presentations, which is what is about to commence. So while a lot of you were out enjoying the break from classes, the teams here were presenting to the judges in the past 2 years. And I believe not only were the judges impressed by the projects, they may have a tough time deciding on the final list of winners. So the students today are going to discuss projects that could impact and improve a number of people's lives, certainly mine: secure browsing on my phone, innovative technology for nerve cell generation so I can be pain-free, collision avoidance system for the visually impaired or for lazy walkers like me, technology for improving driving strategies so I can be a safer driver and save on my costs, and an energy-efficient wheelchair for the disabled, which I hope I won't have the need to use. So during the oral presentation, each team has a maximum of 8 minutes to present, followed by up to 3 minutes of questions. So the final awards are based on both the poster presentation as well as the oral presentation. So after the last of the presentations, we'll tally the judges' ranking, and we'll determine the winners shortly after. So there are some prizes. Some of the teams were asking me, what's the prize? And I said, whatever you win, half is mine. So the first place will receive a $1,000 prize and recognition at the C's graduation ceremony. They receive an additional $200 if their project is deemed patentable or green. Second place receives $500, and the third place receives $200, but each get an additional $100 if it's green or patentable. And the order of presentations were determined by lots drawn by Sandra. So, teams, are you ready to rumble? Yeah. All right, ladies and gentlemen, from computer science, Eli Madsen.
Hi everyone, I'm Eli Matson and I'm here from the Department of Computer Science. My project is Bastion, which is a secure mobile web browser. Now, we all know it's important to protect your information. When was the last time you were at an ATM and you're like, hey, yo, dude, behind me, this is my credit card number and PIN. Just like, have at it, good luck. Honestly, never. Well, what if I were to tell you that online, you can have this exact same thing happen? One of the ways you can do this is what's called a man-in-the-middle attack. Normally, when you're on your device, you're communicating directly to the internet, and the internet communicates directly back. But if somebody manages to put a Trojan or something onto your device, then instead your communications will go straight through that, and they can monitor all of your information. This means they have access to your passwords, to your financial records. They can see everything you're doing, and they can manipulate it as well. One of my favorite Trojans that's been getting tossed around recently is something called Zeus. What Zeus does is it usually gets manifested on your device in something called a drive-by download. That means somewhere there's been some malicious JavaScript, and behind the scenes while you were visiting Facebook or some other fun site, unbeknownst to you, your browser was downloading and putting this little Trojan on there. Zeus can then sit around and wait until you go someplace like Bank of America. There, it can start to siphon off money as you're continuing to check your balance and things like that. Zeus currently is responsible single-handedly for stealing millions of dollars from Americans and other people abroad. And best of all, just last year in May, it went open source. So if anybody's interested and has a GitHub account, you can go download Zeus. Have fun. Obviously, this is a pretty stark image, and mobile attacks are increasing often. But there's a solution now. It's Bastion. Now, like I was saying, normal browsing, all of your rendering is done on the device. This means that when that little JavaScript code happened and Zeus got downloaded onto your phone, well, it ends up on the device because that's where all of your computation is happening. Bastion changes up this architecture a little bit. Instead of being kind of reactive and having to plug up any holes that let people in, we do all of our browsing externally. By doing this, instead of having to render things online, we have a little secure servlet outside on the cloud where this time, when that drive-by download occurs, it ends up out in our sandbox. So you might still be thinking, you're like, great, okay, so it's not actually on my device, but I'm still doing all of my browsing through this little sandbox server. What am I going to do? Well, Bastion, every time you start up a new browsing session, gives you a brand new little sandbox server to browse through. So this way, even if something negative has happened, you'll be safe and you can continue to browse safely. So now let's give a little bit of a demo that'll just show Bastion in action. First, this is Safari. Obviously, as you can see, we're loading up a site and all's going well. But no, we're being hacked. We thought we were logging on to Bank of America. Somebody's already knocked it over, so they're putting negative things onto our devices. So this isn't good, but what you should also pay attention to is kind of take a look at what the site looks like. I mean, it has scrolling. You can look at things. There's some nice images. That's all great. Now let's do the exact same thing via Bastion. Obviously, so what we're doing now is we've just started up a new session in Bastion. Currently, we're loading up the site, and as you can see, it looks exactly the same. But you might have noticed none of the annoying pop-ups showed up, and we're not getting attacked, as it were. That's because Bastion's already caught these things, and it's handled it. And so now you're able to browse and continue to do what you would normally do on your website without even knowing you've been attacked. And by doing this, we can provide a nice, transparent experience for the user. Great. So how did we really do this? Well, we used a technology called sandboxing. And what that does is, by keeping everything externally, sandboxing is used a lot in the security world. You use it to check out new programs or programs you're not sure about. And basically, you isolate all of the processes surrounding that in a separate thing. So a lot of browsers use that already, but they're still sandboxing internally on your device. We do the sandboxing externally to help make sure that things are even a little bit safer. So the main component of Bastion is actually all based out in the cloud. The application is important, but what really happens is out here in the hypervisor, which kind of manages all of these little serverlets that you're dealing with. As each of these serverlets gets spun up, the hypervisor manages all the communication through, which we make sure is encrypted, so obviously you don't want anyone listening in on your browsing. And then we take care of it in that fashion. So then the next challenge is, once we've rendered all these pages out there, we need to make sure that these web pages are clean when we finally do pass the parsed out version. Originally, I was actually only looking at screenshots of the web pages and then trying to do processing from there. But that's not a very efficient user experience, and it's not very much fun. So then we started by rendering it and pulling out all of the source code. Then we take out only the parts we want, those paragraphs, your pictures, things like that. And we only send these items on. We take out any kind of scripts or execution that might happen on your device. And so this way, there's a lot of on loads or on clicks for those of you who are familiar with HTML. And we make sure none of those do anything while they're actually on the device. Now, this isn't exactly, people have been using sandboxing for a while. So Our competition as it is like Sandboxy. There's actually an application on the Apple Store called Sandbox. I was upset. I wanted that name, but Bastion will have to stick. And Spike Security. But the thing is none of these guys actually do mobile sandboxing. Spike Security makes something they call air gap, but really what it is a remote desktop that they then kind of just pass over and let you view kind of via a video interface. So Bastion is kind of the first of its kind that goes out and does an actual like web scrubbing and goes from there. There's a lot of important commerce sites out there. I know I use a lot of them. There's PayPal, Bank of America, Chase, Wells Fargo. You know, the list goes on. These are some of the top sites, and in the last 3 months alone, attacks on banking websites has increased in threefold. So mobile malware is growing stronger. Use Bastion. Browse safely, my friends. Now available for questioning, I believe. All right, sounds good.
Right, from mechanical engineering, Geneva Goldwood and John Johnson.
All right, good evening, everyone. I'm John Johnson. This is Geneva Goldwood. We're here representing the Mechanical and Aerospace Engineering Department. So what we've done here is we want to stimulate nerve growth within the body itself. We've done so by creating a device that consists of a tissued engineered scaffold and an etched optical fiber. The scaffold itself holds a structure and the environment for the cellular growth. It provides a guidance tube so that the cells can grow in a linear fashion, and the etched optical fiber disperses light along its length. The motivation behind this project deals with the fact that nerve damage is very prevalent and that nerves are not able to grow themselves within the body very well. 87% of trauma patients experience some sort of peripheral nerve damage, and 12% happen during surgery. So when a surgeon goes into the body and has to cut through a certain part of the body, they can damage a nerve, and the organism itself can suffer from that. The current treatments to treat the nerve damage happen. The current treatment methods are autograft, which a nerve is taken from the body and transplanted into the donor site. Also can happen is an allograft, in which a human-to-human transplant happens. So if there's a nerve damage inside one human, the tissue can be transferred to that other person. Or a xenograft, in which animal tissue is used. The three of these treatment methods come with their problems. You have limited donor tissue available. The host can be rejected. And also, there's a problem with that 50% of these surgeries fail to have good or even normal return to cellular growth.
In order to overcome the issues of current treatments and to increase nerve regeneration, we decided to apply the concept of low-level light therapy, which was discovered in the 1960s, not long after the invention of the laser. A Hungarian scientist was doing research on lasers in skin cancer when he realized that hair grew back on the backs of rats who had been shaved noticeably faster on rats that were treated with a laser than those that were not. As you might imagine, much research has been done on this since the 1960s. However, everyone irradiates through the skin. This is a problem because of this curve that you see, which is called the Arndt-Schultz curve, which shows that benefit is based on both time and power density of irradiation. Too little of either of these, and you won't have enough benefit. Too much, and you'll have inhibition or cell death. Thus, it is important to control the radiation that's reaching the nerves and to attempt to land right on the peak. So instead of irradiating through the skin, We're irradiating from within the construct, which is within the body, by way of an etched optical fiber. Our fiber was etched using a chemical solution, and our scaffold was created using a 3D printer. The material has been previously FDA approved, and there are channels for guiding cell growth. In addition to creating the product, we had to verify that the scaffold and phototherapy worked. So in the yellow column, you can see that cells did attach and adhere to the scaffold and grow on it. However, you can see from the blue and the green columns that with the laser and LED irradiation for just 5.5 seconds, one time, we saw almost 4 times as much growth with irradiation than without. We also compared 2 different materials, which is 2 different molecular weights of the material that we were using, which is 575 kilodalton and 700 kilodalton. We also compared 2 different light sources because there is debate in the literature about whether you need to have a coherent light source or not. So we also needed to verify that we could etch a fiber. What you see here in the top left is an unetched optical fiber. In the top part, you can see the plain glass cylinder, and it's surrounded by a fluoropolymer coating, which you can see below that. So 2 options that we have are to etch either the fluoropolymer coating, which you see in the top right, or to actually get rid of the fluoropolymer coating altogether and etch into the glass, which you see in the bottom layer. In summary, we were able to prove the concept of an engineered construct for a novel implantable device. We proved the scaffold using our SEM imaging and the cell proliferation testing, and we were able to prove that we could modify the surface of a fiber. We also showed that with just one 5.5 second irradiation time, we were able to get increased cell growth. To move forward with this, we'd need to do further measurements on the power that's exiting an etched fiber, and then we would need to do longer-term cell growth studies with the fiber implanted in the scaffold. So in summary, we have been able to design a novel, feasible way that will hopefully improve the quality of life for people who are affected by nerve damage. Thank you.
Any questions?
What's the scale of the etching that you made on these devices? You 3D printed this, right? Or
Yeah, so the scaffold that you see here, the channels are about 250 microns in width. Yeah. Thank you.
Thank you.
So next, from electrical and computer engineering, Brandon Bonnier and Srinivas Thapa.
Hello, my name is Srinivas Thapa. I'm a biomedical engineer.
I'm Brandon Bernier, a computer engineer, and our project is a collision avoidance system for the visually impaired, which we're calling UltraCast, so ultrasonic collision avoidance system. And we've been working on this with our mentor, Professor Corman.
An overhead branch to us is dangerous. As I walk along, I get spliced on the head or in the face, on the nose. It happens on a daily basis. But round here, I've marked the branches, which I know I'm going to walk into.
That blind man is going to run into those branches. Our goal is to make sure that doesn't happen. So the current market is that there are 285 million people worldwide that are visually impaired. That's roughly the size of the US population. 14% of them are actually completely blind.
Right, so if we look at the current products available on the market right now, really only 2 things that kind of serve to protect the user from hitting these obstacles. The first of which is Georgie Phone. It's an app for Android phones which basically allows a user to mark based on GPS data where they've hit their head in the past. So obviously some drawbacks here. For one, it's an extremely expensive app, so it has some other functions available, but it's $400 for the full app. Obviously, they have to hit their head first before they can mark it to say, avoid this area in the future. And it's relying solely on GPS data. So for whatever reason, if they don't have GPS available, obviously if they're in a new location, they're going to hit their head on everything that's above the waist. So they don't have that same protection.
Another product on the market is called eyeglasses. This tells users about objects on their head level, but only provides vibrations on the ridge of their nose to alert them. There's a learning curve associated with this. You have to figure out what a certain amount of vibration means about the object. So what did we do?
At 4.0 feet, at 2.0 feet, at clear.
All right, so what our system is actually including, so here's a basic illustration of our system. We have a headset that's going to protect the user at the head level, so it's going to detect obstacles at head level. We also have a cane attachment, which is going to basically give the user longer range than what just their cane is providing. So it's adding to the functionality that they already have. And then an application on an Android device in the center to kind of bridge the two together as the hub that can generate audio alerts for the user.
Yeah, like Brandon mentioned, this Android application is going to provide the audio alerts, but it's also going to make sure that there isn't any interference between the ultrasonic sensors and that it launches and connects to these two specific devices without the user having to do anything else.
All right, so just the basic design progression that we went through. So we started with an idea, obviously, and from there we created a basic circuit diagram on the upper left there. From that circuit diagram, we were able to start prototyping on just a simple breadboard, put the components together, see how they were working together. From that design, we were able to progress to an actual printed circuit board. So we laid out that circuit design piece of software and had that actually printed up and fabricated. And then once we got that back, we were actually able to put all the components on. As you can see in the bottom left there, once all the components were placed onto the PCB. And then from there, we wanted to see how this was actually going to operate. So we started creating a headset, had the ultrasonic sensor tucked into the glasses themselves. But at that point, we were just taping the circuitry right onto the side of the glasses. So we said, how could we improve that? And what we wound up doing was creating 3D models of our devices, having those 3D printed so that we'd actually put the circuitry right in there and wind up with an actual clean and compact final product.
So this is the system prototype. It's one step away from being commercially available.
Right, so commercialization, definitely. When we look at the future, where do we see this going? We definitely think it could be a commercially viable product, right? We've already gone ahead, we've filed a provisional patent on it, and if we look at how much we think it might cost for the system that we've created so far, it's about $160 for the parts, right? And definitely we think we can improve upon what we already have. So as far as the peripheral devices goes, we have the headset here, right? We think we could definitely integrate it better. So make this even smaller, more directly integrated into the headset, and also inductive charging. How it works right now is there's a simple USB port on the back where you can plug it in. But for a visually impaired user, actually having to find that, plug it in, if we can do it inductively, they can just take the device, put it on an inductive charging mat, and go from there. It'll be charging right on its own.
In terms of the application, we want the user to have language options. We want them to have alerts in whatever language they're comfortable with. In addition, we want the user to be able to choose the range in which they want either the head level or ground level objects to be in. Definite would be trying to get the app ported to different OSs, such as the iOS or the Windows Mobile.
So we're going to do a simple demo with just the headset so you can get a feel for what the user is actually going to receive as feedback.
So I'm going to launch the app. It's going to connect automatically to those and start giving us alerts. Takes a second to connect.
Connected. Head clear.
All right, so that's telling me that the head is clear. We have it set up
Head 1.5 feet. Head clear.
Of about 5 feet in front of the user that it's actually going to give alerts for. So I'm going to walk at Srinu basically as an obstacle. He's going to put his arm up to kind of simulate a branch. So as I walk towards that,
Head 5.0 feet. Head clear.
Right.
Head 2.5 feet.
So
Head
it's just
2.0
telling
feet.
me
1.5.
what's in front.
Head clear.
And I mean, if you took it going towards something like a solid wall,
Head 5.0 feet. 3.5. 3.0, 2.0, 1.0, head clear.
Able to give the user, rather than just a vibration on the nose, it's telling them legitimate information as to what's in front of them. So real numbers. So something's 2 feet in front of you. It's not just vibrating. It's giving you solid information.
Some other cool things we want to highlight, it does connect, as you saw, automatically without the user having to do anything else except launch the app. Additionally, the battery life for the either device is about 60 hours and rechargeable via micro USB. Questions?
Any questions?
Let's go.
Have you thought about integrating anything else in, like GPS? So I could see, as navigate, suppose somebody does want to go somewhere and they could, if you had navigation information, so they knew, well, I'm at the corner of 21st and I, or something like that.
Sure. That's another feature we would look into, but we believe that Google would try to do that themselves. They have a very well-established GPS mapping system. So if they want to give it accessibility, they could do it better than us, two students trying to figure that out.
It's something we thought about originally when we came up with the idea. We wound up narrowing the scope to just the collision avoidance for the senior design project itself.
What is the angle that it projects out at? Is it straight ahead, or is it?
It's roughly pretty much straight ahead, but we can get about a foot on either side, half a foot to foot. So if there's an object 2 feet away, it could detect it about half a foot to a foot above the head, or half a foot to a foot below, and it's about the same in this plane as well.
Yeah, and it's not just an angle that goes out forever. So that's pretty much directly in front of the user, but then from there kind of narrows out. The sensor itself can read up to 20 feet out pretty much. We're only looking at about 0 to 5 right now to actually give the user that information.
So from my understanding, there's head collision prevention, and then you have the cane attachment,
Yes.
which I assume keeps from tripping hazards.
Yeah.
How does the user, or how does the system differentiate for the user what's going on at the head level versus what's going on at the cane level?
In terms of the algorithm, they don't link up. They are run through the same algorithm, but they're independent of each other. So if the head doesn't see anything, it's not going to say anything. And if the ground does, the ground will alert.
Yeah, so as far as when it notifies the user, if you heard when this was actually notifying me first, what it said was head 5 feet. And then from there, because we were still getting head messages, it just gave me the distance. If we had the ground, the cane attachment hooked up, it would say ground 5 feet, and it would switch back and forth if it was the first reading for that device.
And we made sure that it wouldn't speak over itself. It would finish a full message before giving you the next.
What's the sampling rate of both sensors?
Yeah, so the ultrasonic sensor can take 20 samples a second, so 20 hertz. So it takes about 50 milliseconds to actually take the reading. We calculated out that our response time, so basically from when something is in front of the sensor to when we're actually getting the alert, is about 67 milliseconds. So very quick, we're able to detect something and get an alert generated so the user can hear it.
Does your cane sensor, how about drop-offs, like a curb or at the metro station?
Right now, it's not taking care of drop-offs. So right now, what we have on the cane attachment is the same kind of ultrasonic sensor, but it's set up so that it's always looking straight out in front of the user. If we wanted to, we could add more sensors that could detect drop-offs in the future, but for this situation, just looking out in front of the user. Thank you.
Thank you.
Next, from Civil and Environmental Engineering, Mark Arnoldi.
Hello, everyone. How are you all doing? Good. My name's Mark Arnoldi. I'm from the Department of Civil and Environmental Engineering here, and my senior project was the effects of safety parameters on emissions and integrated car following and fuel consumption modeling approach. So if we look at the motivation for my study, I was mainly looking at a stat put out by the U.S. Department of Transportation in 2006 that says roughly 28% of U.S. greenhouse gases are produced by the transportation sector. Now, considering the hot topic issue of global warming, this is a large, transportation is the largest contributor to U.S. greenhouse gases, so that's a big problem. The other thing I came across when I was doing my literature review, I found that a lot of emission studies are currently taking into account only traffic flow, and at a macroscopic level. Instead, what I decided to do was try to pioneer into considering individual cars and how they affect the emission scheme at a microscopic level. And then I took that one step further by considering, instead of traffic flow, more driver safety behavior. So the objectives of this study were twofold. The first was to bridge the gap between CO2 emissions and microscopic car following models. And the second was to observe the effect of driver safety behavior on CO2 emissions. Now, I accomplished the first objective by creating a program in C++ over the summer that connects the prospect theory-based car following model to a fuel-based emissions model, and use that for the rest of my study. So the prospect theory-based car following model, you can see some of the formulations on this slide. It's based off of economic prospect theory, weighing risky alternatives, creating a utility function, and choosing your decision based off of that utility. And that's seen in the model formulation on the right here. This first equation creates a utility function based off of your desired velocity. The second equation modifies that utility function based off of the probability of crashing. And then the final equation, equation number 3, chooses your acceleration at that time step based off of your maximum utility. Now, in this model, there are also 5 safety parameters of interest that I use throughout my study. And these are the parameters that give us our driving safety behavior. The first one is gamma, the exponent of PT utility. A higher gamma is associated with wanting to achieve your desired velocity, and a lower gamma is associated with being more crash apprehensive. WM is a weighing factor of negative utility. It's a general risk averseness term. WC is a subjective crash rate parameter. It's an indicator of how aggressive you are in near crash scenarios. And finally, alpha is a velocity uncertainty parameter. It's associated with adverse weather conditions, and it's a measure of how well you can predict your lead car's velocity changes. And then beta is a logic uncertainty parameter. It's associated with driver inexperience. Moving on to the emissions model, I chose this model for 2 main reasons. The first was it allowed me to take any make, model, year car that I wanted and model its instantaneous emissions. And then second, it allowed me to get the vehicle characteristics from manufacturing website, which made it easier, and also fuel economy data, which it's also based off of from EPA driving city cycles that you would see on the dealership sticker, those MPG numbers. This model, the fuel consumption is based off of 2 things, the alphas, which are the vehicle characteristics, and the power, 2 equations for when power is positive and negative. Power is based off of resistance, mass, acceleration, velocity, and driveline efficiency. Alpha naught is the idling characteristics of the vehicle, which is why when power is negative, fuel consumption is equal to alpha naught because your car is idling. And then finally, alpha 1 and alpha 2 are determined from the system of equations you see in bullet point 4, and that's based off of that fuel economy data. So the project approach, I ran a bunch of simulation trials, over 1,000, and this involved using 1 lead car, which followed the urban dynamometer drive schedule, which is this figure right here. It's an EPA cycle meant to model urban driving situations, and you can see that there's a lot of stop and go going on and a lot of acceleration differences, which was very useful for my project. The following car, one following car, its trajectory was determined by the prospect theory, which I described earlier. And then each run individually varied the 5 safety parameters that were discussed from 20 to 200% of their typical values. And each trial was rerun for 3 representative cars, the 3 cars here that were chosen to run the gambit of vehicle sizes and classes. So here you can see some of the acceleration results. The y-axis here is the changing parameter value. The x-axis is acceleration values. And the colors are showing the frequency with which an acceleration value was chosen over a run. A darker red indicates more frequency. A darker blue indicates less frequently. So of importance here, you see gamma and WC. They have these dark red lines that go all the way across the changing values. They didn't really have an effect on emissions. However, if you look at alpha, WM, and beta, you see that there's a lot more colors in their graphs, their distributions are wider, and their peaks are less clearly defined. When we change these values, the chosen acceleration values of the following car differed, and that had a major effect on emissions that you can see here. So the y-axis on this is total CO2 emissions throughout a run. The x-axis is the changing safety parameter, and then there's 3 graphs for the 3 representative cars. Again, looking at gamma and WC, you see these lines are relatively horizontal because changing these parameters did not have that much of an effect. However, looking at beta, WM, and alpha, you see that increasing alpha causes an intermediate increase in emissions. Increasing WM causes a very large increase in emissions, about 10 grams. And then at very small values of beta, you get a small increase of emissions. It's kind of like a threshold effect. So looking at the conclusions and bringing that back to the physical meanings of these parameters, again, gamma and WC resulted in little to no change in emissions, but driver inexperience associated with beta had the smallest effect on total emissions, but it was significant. Adverse weather conditions associated with alpha have more of an intermediate effect on emissions. And finally, being risk averse, WM caused the greatest increase of emissions. In general, we have to find a balance between being risk averse on the roadway and wanting to achieve our desired velocity if we want to decrease overall emissions. And finally, creating a driving environment with fewer high-risk behavior and a more uniform velocity flow pattern will decrease the effect of the transportation sector on the environment and on those greenhouse gases that we talked about at the beginning. The future of this study, it has a lot of potential, especially with an expanding need for intelligent transportation systems and automated vehicles. That's where I kind of see this project going, eventually being used for a eco-drive feature in an automated vehicle and determining the algorithm that makes the decision on acceleration based off of emissions, driver safety, and finally, your desired velocity in getting to where you want to be. So, are there any questions? No? Okay, thank you.
And finally, from Biomedical Engineering, we have Daniel Gill and Ben Nakamura.
Hello, I'm Ben Nakamura, and I'm an electrical engineer.
And I'm Dan Gill, and I'm a biomedical engineer.
So the goal for our capstone project was to create a wheelchair, which is not everybody can use standard wheelchair. So we wanted to create a wheelchair which everybody could. Our result is a smart wheelchair. Last year I was involved in the solar decathlon team. We built a home for wounded warriors. I really wanted to create a power wheelchair which would work in that home.
Since my background is biomedical engineering, I wanted to make sure that this wheelchair was usable by the greatest number of people, no matter what their disability. I quickly realized that voice recognition is one of the most accessible methods, but there's an inherent problem with voice recognition. There's a delay between when you say a command and when the wheelchair starts to respond. To ensure the safety of the user during this time, we also implemented a collision avoidance system, which we'll talk about more. Through our literature research, we found that estimates of about 2.1 million people as of 2008 would benefit from such a wheelchair. These individuals suffer from overlapping physical, perceptual, and cognitive symptoms that can stem from a number of diseases such as Lou Gehrig's disease, traumatic brain injury, spinal cord injury, and cerebral palsy. Currently, individuals with the most severe symptoms require 24/7 caregiver attention to get around. People may have seen, people may know the case of Stephen Hawking, who has Lou Gehrig's disease. He was fortunate enough to have a custom wheelchair built for him, but most people aren't that lucky.
So this is our system. A person in a wheelchair gives a voice command. This voice command is then taken over to the user interface. It then checks the sensors to see, just to ensure that those sensors are not violating the command. And then if it's not violating the command, they're passed on to the electric control system, which then takes that command over to the wheelchair and does it. So I'm going to give an example of one of these commands. So if the wheelchair is going forward and there's a wall in front of it, it'll immediately stop. If somebody passes it, then it would stop for an instant and then continue going at its original speed. On the other side of this system is the power management. The power management, it was really important to me to have solar panels to charge this station. So that's the primary way of charging the batteries. We also have an AC charging station just in case the sun isn't shining that day.
So I wanted to take you through the human interface aspect. As I mentioned before, we used voice recognition. Essentially how this works is a voice command from the user is spoken into a microphone that is connected to a laptop. The laptop then processes this command and then communicates with the rest of the system via USB. So not everyone, I'm sure most of you have used voice recognition. Most smartphones have this functionality, but this is just how it works. Essentially, you start with an activation word. We use chair. Google uses OK Google. And then the rest of the commands. So for example, if we wanted to turn right at 90 degrees, we would say chair hard right. We tried to limit the vocabulary to make this as user-friendly as possible. So the other aspect of the user interface is the collision or obstacle avoidance. We used 8 ultrasonic ranging sensors placed around the wheelchair. On the left here, we have where the sensors are placed on the wheelchair. So this is to make sure that the safety of the user is maintained. What this is basically compensating for is the gold standard input method for power wheelchairs is a joystick, which reacts very quickly to a number of different circumstances. But voice recognition is slow. So we wanted to check around the wheelchair to make sure that we didn't run into anything.
We're running tight on time, so we're just going to go over one advanced movement. So we're going to go over the follow right. So this command allows the user to actually follow a person walking next to them. If they're directly next to the wheelchair will continue its original pace. If the user steps in front of it, then the wheelchair will actually increase its pace. And once it's caught up and it's back in line, it'll just be going at the same pace as the walker. But if he falls behind, then the wheelchair will actually decrease its pace. So the solar charging station. This is a 60-watt panel. In the future, if we commercialize this, we would be using 120-watt panels, just so the solar panel can actually charge one of the batteries in one day.
So there are a lot of advantages to our project. The modular design allows the human interface to be swapped out interchangeably. For example, if a specific user can't use voice recognition, we could sub in eye movement, head movement, tongue selection, and another way that we could do the voice recognition is via smartphone, and then it would communicate with the electronic control system via Bluetooth. So we thought about different ways we could commercialize this. One of the main points that I'd like to make is that there are no smart wheelchairs available in the US market. So we could market our project as a modular plug-and-play kit that would consist of the microcontroller, the power electronics, the solar charging station, the human interface, and the collision avoidance system. And we believe that we could do this for under $500. We also have multiple international marketing options. Mechanics in developing countries who have a high level of technical skill could implement our plug-and-play module, our plug-and-play kit to repurpose existing power wheelchairs in that country.
We just want to say thank you to everybody, especially Professor Manusha for mentoring us. And we would just want to highlight that this has been a project from design to actual completion of the project, so we were able to implement it. And this really had a lot of different types of engineering involved in it: electrical, mechanical, biomedical, and yeah, finally, thank you to all the mentors that helped us along the way.
Are there any questions?
Well, now we come to a kind of an interesting part of the program, because either the results are available or they're not. Does anybody know? They're not. Okay. So, you know what it says on the script for me? It says the dean provides filler until the results are ready. So what should we do for filler? Sing? Dance? Pop quiz? But Susan mentioned something that's very important. She talked about giving back, and she mentioned that if you go to the GW website, there are a lot of boxes to choose from. But there's really only one there to choose from. And it has 4 letters there, and it says S-E-A-S. That's the one, folks. Yeah, you can contribute to athletics or something. I'm not bullying you, but C's is the one. That's fine. So what, and another acronym came up in Susan's speech, and what was that? Yes, but what else? You said it in a sort of a little bit of a disappointed way, didn't you? The SEH. What about that SEH? Have everybody been watching it? I mean, we're now about 6, 7 months away from moving in. That's really phenomenal. You said you've waited 4 years. I've waited 6. I got here 6 years ago almost, and I've been waiting, and I'm really excited to be in there. And all I can say to you graduating seniors is this, and it's a little bit lame and it's a little bit weak, but it's actually true, is that the SEH is enabling us to build a stronger school with new faculty, with growing enrollment in our PhD programs, our master's programs, our undergraduate programs. And what that does is strengthen your diploma. So 10, 15 years from now, when the school is considered to be much stronger than it is today, your diploma will be worth more. So although you never got a class in the SEH, you got a stronger diploma out of it. And incidentally, with respect to admissions, we will have, if all goes well, this coming fall, we will have the largest freshman class we have had in 130 years of existence as School of Engineering Applied Science. Enrollment at the freshman level, by the way, is up 40% over 4 years ago. Not at freshman level, overall in Cs. Master's program is also up by about 40% over that same period. I'll go back to annual giving and giving in general, because that's a topic very close to a dean's heart, because that is money for scholarships and fellowships and student support. Giving to the school over the last 5 years has risen by a factor of 5. Our annual giving now is running at close to $5 million a year, which is going in to support all sorts of activities. And that correlates with a growing, stronger school. And as we grow stronger, we hope we engage more alumni and the alumni give back. So if you were the dean and you were up here, what else would you talk about? What about those faculty we've recruited? You, seniors, you've had a lot of them in your classes. For those of you who are visitors and guests here, in the last 5 years, we've recruited 40 new faculty into the school. That's tenure or tenure generally or tenure track faculty. We have about 89, 90 tenure track faculty. So if you think about that, we've changed out about 50% of the faculty over a 5-year period. Some departments have seen greater change than others. I gave a talk at lunchtime to the University Research Advisory Board, and I pointed out that MAE, Mechanical and Aerospace Engineering, was leading the pack with this rejuvenation, that that department, just 1 minute, I'm providing filler. The envelopes are ready, but the dean is on a roll with the filler. The MAE department has 21 faculty now, and 18 of those faculty have been here fewer than 5 years. We've really turned over that department. And the effect that has is if you look at the variety of research now that's going on and the different and new classes in that department, that's quite remarkable. And the reputation of the department has grown too. Because over this last 4 or 5 years, in the reputational rankings out there nationally, the MAE department has gone from way past 100 to tied for 8th place for 60th in the nation, 40 slots up or more in a 4 or 5 year period. That's what we're wanting to do for every department. Somebody mentioned Google and autonomous cars, right? One of the young faculty in computer science we recruited for 2012 has $1 million grant from Google looking at autonomous vehicles. So that's dear to our hearts. Let me see, I had a lot of other filler material, but I think we'll just get straight to the winners, Sandra. I have engineer jokes, if anybody would like engineer jokes. They're few and far between, but there are some good ones. Okay, for 3rd place, we have Daniel Gill and Ben Nakamura of Biomedical Engineering for their project entitled Energy Efficient Electric Wheelchair. Dan and Ben will receive $200 plus an additional $100 because their project has been deemed green. So congratulations to you. Second place award goes to Brandon Bernier and Srinivas Thapa of Electrical and Computer Engineering for their project entitled Collision Avoidance System for the Visually Impaired. Congratulations. Brandon and Srinivas will receive $500 plus an additional $100 because their project has been deemed patentable. So congratulations. And first place award with the virtual drum roll is Geneva Goldwood and Jonathan Johnson of Mechanical and Aerospace Engineering. For their project entitled A Tissue-Engineered Scaffold and Phototherapy for Nerve Tissue Regeneration. Geneva and Jonathan will receive $1,000 plus an additional $200 because their project has also been deemed patentable. Wow, that was exciting. Congratulations to all the winners. Congratulations to all the participants.